Okay, good. And then let's go full screen. Okay, so welcome everybody to this third week of classes on data mining or data science. And before I start, I summarize what we just were talking about passing this course. So if you need the certificate that you have passed this course, what we are going to do is that you need to have 75% participation of these lectures, first of all. And then at the end of the course, there are some problems like homeworks or assignments on the webpage of the book that we wrote, and I will give you, of course, again the link when we get closer to the end. And I will select a couple of problems from there, which are related to the topics that we touch upon in this course. And so then what you are asked to do is to take those problems and write your own code to solve. So it is important for me to see that you have understood, that you don't use like a packaged code, because that's not really measuring whether you have understood or not. So the idea is that you write your own code. So basically these algorithms that we are doing here, they are rather straightforward to implement. And if you really want to understand what's going on, you should implement yourself, not using, canned program packages, because that's not really like what we are trying to do here. And so then I'm asking you to test your code with some data sets which will be available for you, and you write a report. And so so please try to do it yourself. So that's the best way to measure if you have really understood and digested the topics. So do the programs yourself. So and write the report. And so then I will quickly go through the reports and see if the results are sort of what they should be like. And since I won't have time to do careful feedback process with you, I will rather quickly check that the performance is above what is acceptable. And so then if it is, then I'm happy to give the certificate that you have taken this course. Okay, so I will put this everything in writing, where I also give you the problems and the data sets that you are supposed to look at, and so then you can test, and we'll see how things go. So reporting means that it's not only that you are dumping the code, so that's not really considered the report. So report means that you explain what you're doing. There may be pieces of your code. This is the standard thing that we are doing with this course in our university. So you have to explain what you're doing in let's say plain English, and then maybe pieces of the code, and then graphics is important, because lots of the data science methods is the visualization. And so therefore, so if you're working in applications, you need to communicate with people who are not mathematicians. And so therefore, you need to learn to communicate and explain how you interpreted the data, what you did, and what the results are in a language which is understandable for a non-specialist in mathematics. And so graphical explanations are very good. And so okay, but I'll try to write the let's say the guidelines for you, so that you know exactly what is expected. Okay, so that's what I'm going to do later. So this week we have only these Tuesday classes. On Thursday I will be out of town and I will not be able to access the internet. And so then next week and the week after we will have 2+1 classes. Let me see, there are people. Okay, just a moment. Looks like there's somebody who's trying to get in. How am I going to do this?
Erkki, there was something asking to be connected to the meeting, but I did it.
Yeah.
Usually, you go to the. Can you see the icon with the two people just on the left of the on the left of the chat? Okay.
Yes.
There you have all the participants.
Okay.
And then in the list, at the end of the list, you have the people that want to enter.
Okay, yeah.
Okay.
So,
but I admitted that person. Okay? So you don't need to do anything. I guess.
Okay. Yeah, I don't see any. Yeah. Okay. So thanks for doing that. So perfect. Yeah. All right. Good. So I'll go back to my screen sharing. Okay. Okay. So. Here we go. Yeah, so as I said, this Thursday we don't have the lecture, but then we will return the week after, and we have 2+1 lectures in 2 of the following weeks. And so I'm trying to cover all the material that I'm planning to cover. So the topic today is an algorithm which is called a support vector machine, SVM. So support vector machine is a classification algorithm, and at first sight it looks like it's something that is very, very restricted. So it looks a classification algorithm that works only for very, very specific data sets. And when I saw that first time, I thought, well, this algorithm probably is not particularly good. Then it turns out that it's one of the most popular classification algorithms, and so I thought it is a good idea for you to see it. Now, the power of this method will be obvious for you later on when we are talking about the so-called kernel extension of it. So I'm going to go through this support vector machine algorithm in its plain simplistic form, as you would call it, and so then at the end, or maybe next week, if I will not have time enough to do that, we will go through the famous kernel extension, which make it so powerful and popular algorithm as it is. Okay, so what is the starting point? So the support vector machine algorithm assumes in its primitive form that you have a training data which consists of 2 clusters, and in this picture you see the red dots and the blue dots. So that's my training set. So training set means that somebody has gone through the data and has labeled every data point in 2 clusters. So you can say that they are like well, the labels are usually in vector support machine is +1 or -1. So you have 2 classes, and each point has been classified by an expert to be in one class or another. So you can think it's a medical sample, and you have benign and malignant sample, for instance. So there's an expert who has looked at the data and said, well, this corresponds to malignant and this corresponds to benign, for instance. So that's one example. And so having that training set, you try to find a hyperplane that ideally separates the 2 clusters. So you try to find a plane that cuts through your dataset training set so that one type of points are on one side of the plane and the other type of points are on the other side. Now, what kind of data is that? So usually when you have data, the data is not organized that way. So therefore I thought, okay, so the support vector machine is very limited. But it turns out that it is much more versatile than it looked like from the outset. Now, classification means that first of all, you once you have found this plane, this yellow plane that separates your training data into clear-cut clusters. So when a data with unknown annotation comes, what you need to do is check which side of the plane it is, and according to how you had your training data organized, you classify the new point in one of these clusters. So that's the classification algorithm. So it looks very, very simple. And also, as I said, it looks very, very limited. How can that work? So this algorithm takes you into to the optimization world. So the algorithm is based on a certain primal dual optimization approach, and since this is a little bit different from what we have done so far. So the algorithms that we have been using and looking at so far, PCA, LDA, SOM, they are all approaches where let's say there is no optimization component really. So you just straightforwardly use either linear algebra or updating schemes. So you didn't really have to go into optimization algorithm, but with this SVM support vector machine, you need to dig into the optimization algorithm to understand how it works. So I'm going through this primal dual algorithm rather in detail so that you see how it works. At the end, the algorithm is not that difficult to implement, but before you arrive there, you need to do a lot of technical work to understand it. Okay, so this time we are going to do a little bit of optimization, constrained optimization. Okay, so I start with some fundamental concepts, and the first thing is hyperplane. So everybody knows what a plane is. You are in 3D space, and a plane is a two-dimensional object, which is sort of a linear or affine structure. So that's what a plane is. That's the common sense plane. If you are in two-dimension, plane is replaced by a line. And so if you are in Rn, then we need to define the concept of hyperplane, and hyperplane is n-1 dimensional affine subspace. So hyper means that one spatial dimension has been removed. So in 2D, you have a line because you take off one dimension, and in 3D, you have a two-dimensional plane because you take one dimension off. And in Rn, we are talking about n-1 dimensional subspaces. And so to characterize a hyperplane, as in the picture here before, all you need to do is to define a vector, which is this black arrow there. So that black arrow is perpendicular to the plane. And then you need to tell at what position along the line, which is perpendicular to the plane is. And so you need two quantities. First of all, you need to have a unit vector, omega. So omega is a unit vector in Rn, so the length of omega is 1. And then you need one parameter s. And so now we have the definition of h omega s. So that is a hyperplane parameterized by a unit vector and a real number s. And the definition is you take all the x's for which the inner product omega transpose x equals s. Geometrically speaking, that means that you take any vector x, you think this vector x as a position vector of a point, okay, and so then you take the projection of that vector to the direction of omega, and so then you measure that the component, which is s, is constant, and so that's what defines a hyperplane. So let's go to this picture. So you take any point in this yellow plane, and you project that point to the direction defined by this black arrow, and you see that the component of the vector is always the same regardless of where on this yellow plane you are. So that's the very definition of hyperplane. So hyperplane is characterized by saying that you take all the points which have the same component when you project the component, the vector to a given direction. And so changing omega changes the orientation of the plane, and changing s moves the plane parallel in a perpendicular direction to the vector omega. So here is another picture. So here is my vector omega. So there is a direction, the red line, and h omega s means that when you take the component to that red line, that's constant. Now, if you take any vector x in the space, what you can do, you can always calculate the projection of x to that direction omega. So remember, in the first lecture, we were talking about projections. And so now you see why they are important here. So you project your x to the direction omega. So that's the part of x which is parallel to omega. And so then you add and subtract that projection from your x. And so adding it gives you this t of omega, where t denotes omega transpose x, where t is the component of x in the direction of omega. And then the remainder, x minus the projection, I denote by x perp, perpendicular. So this x perp here is a vector which is orthogonal to omega. So we are decomposing a vector in two orthogonal components. One is parallel to omega and the other one is perpendicular to it. And so for any x, you can always write this decomposition. And so how you calculate it is given in this slide. So t is simply the inner product of omega t times x. And so if this t equals s, you are on this plane, this yellow plane. And if t is not s, then you are in a plane which is parallel to this h omega s, but it's not the same. So that's the idea. Okay, so we need to define distances of point from a hyperplane, and we need to define distances between parallel hyperplanes. Okay, so that's the next thing. So let's look at the distance of a point from a hyperplane. So suppose you have an x which is not on the hyperplane. So my x is an arbitrary point in Rn. And then I have a point y, which is in the hyperplane. So y is in this hyperplane. So what does it mean that y is on the hyperplane? So when I do this decomposition of y into the component which is parallel to omega and the perpendicular component, then the component of y in the direction omega is equal to s. If I take my x, the component of x in the direction of omega is t, and this t is not necessarily equal to s. But so they both have the same type of orthogonal decomposition. And so I write those x and y in that way. And so then I'm looking at the distance between x and y. And I'm looking at the distance squared. So plugging in these x and y decompositions, I get that this vector x minus y is t minus s times omega plus x perpendicular minus y perpendicular. So now we are using Pythagoras theorem, saying that if you have a orthogonal triangle, so the length squared of the hypotenuse is the sum of the lengths of the cathets. And so since omega and x perp, omega y perp, they are orthogonal, so we are looking here at the length squared of two orthogonal vectors. And so therefore the sum is the square sum of those perpendicular vectors. So there's equality, and t minus s omega has the length t minus s, and so therefore this is t minus s squared because omega was unit length. And then we have this length of the perpendicular, the difference of the perpendicular components. Well, the sum is of course larger than one of the components of the sum because these are non-negative numbers, and we see that the equality here holds if and only if the perpendicular part equals the perpendicular parts coincide. So if x perp equals y perp, then this x prime minus y prime has length 0, and we have equality here. So t minus s squared is a lower bound for the distance between x and y squared, and equality holds if I take the perpendicular components to be equal. So therefore, this is really not the lower bound, but it is the minimum, because there is a way to reach that minimum by choosing y so that this perpendicular component equals the perpendicular component of x. And so therefore, what I'm doing here, I'm defining the distance of my point x from the hyperplane by saying that it is the minimum over all y's in the hyperplane of the distance between x and y. So this is the minimal distance of x and any point in the hyperplane, and we just saw that this minimal distance is t minus s. So when you have if you have a hyperplane which is characterized by number s, you calculate the component of x in the direction omega, and then the absolute value of t minus s is giving you the distance of x from that hyperplane. Okay, so that's simple geometric statement, but that's how you calculate it. And so what is the minimizer? The minimizer is the orthogonal projection of x onto this hyperplane. And as we saw, the minimizer is the y which has clearly the component equal to s to guarantee that it is on this hyperplane. And then the perpendicular component has to be the same as the perpendicular component of your vector x. And so you choose this y, and so this y represents the orthogonal projection of x on that hyperplane. So far, I hope everybody is happy. So now, suppose you have two hyperplanes which are parallel. How do I know that they are parallel? Well, if the omega is the same, then the hyperplanes are parallel. And they are different hyperplanes if s indices are different. So s1 and s2 may be different. Okay, so now here's the picture. So we have the perpendicular direction omega, and so these planes are perpendicular planes which we can move along this direction of omega without changing the orientation of the plane. And when you're moving the plane, then the parameter s is changing. And so when I take two hyperplanes, I define the distance between those hyperplanes by taking the minimum number of the norm x minus y, where x belongs into one hyperplane and omega y belongs to the other hyperplane. And so it is not hard to see that this minimum is simply based on the previous argument. It is equal to s1 minus s2. So if I take any point x from h omega s1, the distance of x is from h omega s2 is s1 minus s2, and that's the same distance for all x's in that plane, and so the minimum is automatically s1 minus s2. So if I have that parameterization of hyperplanes, then it's very easy for me to immediately decide what the distance between those hyperplanes are. Okay, so let's go to the classification problem now. We have all the tools to do the classification. Then we start grinding through the actual algorithm, the computational part. And so we have the so-called annotated training data with binary classification. So my data points are x1, x2, etc., xp. So those are my data points. So I have p data points in Rn, and to each x I have associated a classification. So x1 belongs to either class 1 or class 2. For convenience, this classification, as I said in the beginning, is going to be +1 or -1. So you can think that +1 is the red dots here, and the -1 are the blue dots. So you can think this is sort of a heat map, and so the red one are the hot ones, which are plus, and the blue ones are the cool ones, which are minus. And so that's how we classify. So each one of these red dots has a classification +1, and each one of these blue has -1. So let's see what the component of each component is in the direction omega. So since this omega is pointing into the direction where I have the positive, the red points, so therefore I can conclude that the component of any of those red points in the omega direction is larger than s, because we are further in the direction of omega, while the component of xj in the blue set is less than x because we are behind the direction in which the vector omega is pointing. And so I can characterize my data by saying I have two classes, x1 is two classes of points xj, and so those ones for which omega transpose xj minus s is negative, they are in the blue set, and the red ones are in the, so the positive one is on the red set. So this of course assumes that such a plane exists. So if I give you a data set which is annotated, there is no guarantee that you find a hyperplane that is nicely dividing your data into two sets, like in this hypothetical situation. But so that's the starting point. So we start by assuming that this is possible, and then we see what happens if this is not exactly true. We try to do the best. So we try to do as well as possible. But so ideally, if you assume that the classes are linearly separable, then such a plane exists. And the matter is how to find that omega and how to find that s, so that you have this nice classification. So that's part of the problem. Now, so what would you do? Suppose I tell you that your data is indeed such that there is a nice separating hyperplane. So what would you do to find omega, the orientation of the plane, and s, which is the position of the plane, so that this classification works? Well, let's start by introducing a couple of other concepts. Just a moment, I need to do something here in my office. I'm sorry. Okay, so let's continue. Okay, so suppose your data set is such that it is really divided into clear-cut sets by a hyperplane. So then what you can do is you can, first of all, we can try to find the distance of the data set from that hyperplane. And we are looking for the distance of the red points and the blue points from that hyperplane. So let me see. Sorry, I just got a message that I needed to take. Okay, so h1 is the distance of the blue data points from the hyperplane. So suppose you have this hyperplane, you have omega and s. So then you're looking at the distances of each points xj from that hyperplane. And remember, this omega, this should not be perpendicular, this should be the transpose. I tried to fix that, so this is a typo. So omega transpose xj, that is the component of xj in the direction of omega, and so we are looking at the distance of xj from the hyperplane by just taking the difference between s and the component, and so we are taking the distance of all points belonging to the negatives at the blue set, and so that means that we are calculating the minimum of that set of numbers. this is a finite set of numbers, so the minimum exists. So you have just a finite set of numbers and you take the smallest of those. And again, here is another typo, so I really need to fix this slide. So this is confusing. So since we are in the negative data set, omega transpose xj is smaller than s, and so therefore if you take the absolute value here, the absolute value is s minus omega transpose xj. Okay, so because s is larger than omega transpose xj, so the component is smaller than s for data points belonging to the blue set. And there's another typo in the next row. So sorry, this is really full of typos. These slides, this is horrible. So during the break, I'm trying to fix this. Okay, so h plus is the distance of all points which belong to the red set, and so we take the x omega transpose xjs when xj is in the red set, and so now omega transpose x is larger than s, so therefore the minimum is the absolute value of x transpose xj minus s, and so here should be plus, so cj equals +1. Okay, so I need to remember that this is full of typos, this slide, so I'll fix that. Anyway, so I hope you understand regardless of the typo. So h1 is the distance of the blue points from the plane, and h plus is the distance of the minimum distance of all points in the blue set, and h plus is the minimum distance of the red points from the plane. And so now we can try to adjust our separating hyperplane so that it has equal distance from both clusters. So since these distances are assumed to be positive or zero, at least one of them is positive, assumingly. Well, it's not even necessary, but so you can think that you're adjusting your hyperplane in such a way that it's equally far away from the red set as it's from the blue set. So I'm adjusting my plane right in the middle of those two data sets. Okay, so sorry about the typo. So I tried to explain here the picture. So given this hyperplane h omega s, we are defining h minus and h plus as two hyperplanes which are parallel to my h, and they are at the distance h from my original hyperplane. So my hyperplane that I'm using as a separator here is this yellow hyperplane. And so on one side I have the blue dots, and on the other side I have the red dots. And so I'm measuring the distance of the red dots and blue dots from my hyperplane, and I'm adjusting the position of my yellow hyperplane in such a way that it has the same distance between the red and the blue data set. And I'm placing parallel planes, h plus and h minus, on both sides of my separating plane, so that the distance between those planes is h. So this is sort of a symmetric adjustment. So all the positive points are beyond that h plus, so away from me, and all the blue points are closer to me than this h minus. And this yellow plane here is dividing the data sets in two. So that's the geometric construction. Now, what we are trying to do is we are trying to find this omega and s, so that this construction is corresponding to the division of the data. We do a reparametrization of the hyperplane. So it turns out that there is a reparametrization of these hyperplanes which is more convenient from the point of view of calculations. And so I'm explaining here the reparametrization process. So let's look at those planes h plus and h minus. So h plus and h minus, the hyperplanes are defined as hyperplane perpendicular to the direction omega with the component parameter being s plus or minus h. And by definition, this is the set of x's in Rn with the property that that omega transpose x equals s plus minus h. So this is the very definition of these hyperplanes. Let's look at this condition, omega transpose x equals s plus minus h. So it is copied here. So omega transpose x equals plus minus h. I divide this equality by h. So I get 1 over h times omega transpose x minus s divided by h equals plus minus 1. So what I wanted with this reparameterization, I wanted that I have plus or minus 1 instead of plus or minus h here in the right hand side. And then I make a change of variables here. So I'm defining q to be a vector which is parallel to omega, but it is no longer a unit vector. So I'm taking this q to have the length 1 over h. And so notice if h is small, this q is a long vector, but it is parallel to omega. So the important thing of q is that it defines the direction still of the hyperplanes. And I define this b parameter to be a real number, which is s divided by h. And so now I'm reparameterizing my planes. I'm defining planes h plus and h minus as planes which are parameterized by the numbers q and b. So if you give me q and b, I can define two hyperplanes with the following way. I take x in Rn and I calculate the inner product of x with this vector q, subtract this b, and so you should get plus or minus 1. And so if you get plus or minus 1, you are in one of those parallel separating hyperplanes. Okay, so this is, I'm not changing the geometry at all here. I'm simply changing how I'm parameterizing those hyperplanes. So instead of using a unit vector, I'm using a vector q, which is no longer a unit vector, and I'm using a variable b, which is s divided by s divided by h, and so I'm defining the parameterization like h plus minus in this manner here. So that's my reparameterization of those two planes. So eventually what I'm trying to do is I'm trying to find the vector q and the parameter b in such a way that these hyperplanes h plus and h minus have the largest possible distance from each other. So I'm sort of maximizing the gap between the two data sets, and so that the gap really separates the two clusters in the data set. So here is a picture. So I'm taking a side view of this situation. So I have the blue points here, and I have the red points here. So they are the annotated data, my test data. And so then I have a yellow zone here, and this is a gap between my two data sets. So this is the ideal case. I'm assuming that my data is such that there's a clear gap between those two data sets. And so then I'm taking the vector q, which is no longer a unit vector, it is just a vector of some length, so that these hyperplanes, the blue hyperplane and the red hyperplane are perpendicular to this q. And so the blue hyperplane here is a plane that is having all the blue points to the left of it. And the red hyperplane is such that all the red points are to the right of that hyperplane. And so here is the equation of the blue hyperplane, q transpose x equals b minus 1, and the red one is q transpose x equals b plus 1. And so notice I have denoted by a little rectangle some of the points. And what are those points? Those points are the points which were closest to the original dividing hyperplane. So remember, my original hyperplane was somewhere in between here, in the middle, and then I created two artificial hyperplanes on both sides so that the blue hyperplane, which is the H minus, is just barely touching my blue data set, and the red hyperplane H plus, which is barely touching my red data set. And so there are two vectors here in this picture which lie on the hyperplane. And so those two vectors are called support vectors. So that's where the name support vector machine comes from. So it's funny name this machine because this is really an algorithm. So people who came up with this idea, so they had sort of a support vector algorithm that they decided to call it a machine. So the support vectors are these vectors which are lying on the hyperplanes, which are separating the two data sets. So if you look at this picture, there is no direct indication what the distance between those two separating hyperplanes are, because I did the reparameterization. But so we can easily calculate, if I know Q and I know B, it is easy to calculate the distance between these two hyperplanes. Namely, Q was defined as 1 over h of omega. Okay, so an omega was a unit vector, so that was the original definition. The omega was originally a unit vector. Now, the distance between those two separating planes is 2 times h. And if you look at this definition of Q, you realize that the length of Q is length of omega, which is 1 divided by h. So it is 1 over h. So therefore, h is 1 over the length of Q. And so since the distance between these two hyperplanes was originally 2h, so now in terms of this new parameterization, I have that the distance is 2 over length of Q, and here should be h minus and not h1. So again, a typo. So I try to remember to correct that too. So the distance between h1 and h minus is 2h, which is 2 over Q. Okay, so good to know. If you give me a Q, I can calculate the distance between these two planes. So let's look at the conditions that are characterizing my data points. So let's go to the blue points here. So we see that the blue points are to the left of this plane Q transpose X equals B minus 1. So that means that if you take the component of any xj in the blue set, then this Q transpose xj minus 1 minus B has to be less or equal to minus 1. Because on the hyperplane it is equal to minus 1. If you go to the left, which is in the opposite side to where the vector Q is pointing, this number becomes smaller. And so therefore, instead of being minus 1 when you're on the plane, you get something which is less than minus 1. So this is for the blue set. Now, if you are in the red set, then on the red hyperplane, Q transpose xj minus B is equal to 1. But since we are moving in the direction where the vector Q is pointing, this number is larger than 1. So these are the conditions that are characterizing my two clusters. And now you see why we use the classification index to be minus 1 or plus 1, because it gives us a very nice way of expressing these two inequalities in one single formula. Namely, if I multiply both sides by Cj, the lower one doesn't change at all because I'm multiplying by 1. If I multiply the upper inequality by minus 1, first of all, the direction of the inequality changes and minus 1 becomes 1. And so you can see that I can combine these two conditions by saying that if I have this separating gap between my data sets, then Cj times Q transpose xj minus B has to be larger or equal to 1 for all points. So this is the condition that is valid, supposing that the data is as I expected it to be. No, that's good. So how do we try to find this Q and B then, so that we have the best possible separation? So suppose you know that your data is linearly separable, so that the assumption is true. So then you can define the following optimization problem. You try to find Q and B in such a way that the width of the gap between those two sets is maximized. Well, the width of the gap was 2h. Now, we saw how to calculate h. In the previous slide, we said that h is 2 over q, the length of q. So what we are doing, so suppose if you want to make this q as large as possible, what you need to do, you must find the vector q so that its norm is minimized. So if you minimize the norm of q, then you are maximizing the width of the gap here. So that's what we do. So we say, let's try to find a q so that it has the minimum possible norm. So I'm minimizing 1/2 of the norm of q squared, subject to c j q transpose x j minus b is larger or equal to 1. Again, a typo. So the subject to condition is that this inequality holds. So there is something missing here. Again, I try to fix this during the break when we have one. Okay, sorry about the typos. This is late night editions, and so typos are inevitable. So okay, so we are minimizing the length of q subject to this condition here, which is in the box. Okay, so that's our goal. Now, it may well be that the data is not linearly separable. And so what should we do then? So how do we deal the case when the data is not separable? So let's go through the data points, and let's classify the data points in two classes. So you have those data points for which the separability condition is valid, and I'm going to denote by J capital the index set of those data points which can be separated to one side of the plane, and so that this condition is hold, and this condition holds. And so if it doesn't, then I say that J belongs to the complement. So this is a little bit circular because what is first and what is second. So suppose I have a Q and I have a B. So suppose I have a plane and I have a B which defines so Q and B, so that we have this gap situation. So I'm checking whether the data points are on the right side of the gap, and I'm denoting by J capital those points which are on the right side of the gap, and J complement is the index set pointing to the data points which are not on the right side of the gap. So I may have some outliers, some points which are not classified correctly. So they have ended up on the wrong side of the gap, and so those data points are listed with J belonging to this J complement. And so then, as it's often done in optimization problems, I'm defining when you have inequality constraints. So you write the inequality in form of an equality. And so I'm going to define this zeta j, which is called a slack variable, which is defined as 1 minus cj qt xj minus b. And so notice, when you have a point which is not obeying the classification rule, then this number may be positive. So I'm defining this zeta j to be this positive number here for those points which are not obeying the classification rule. And if the point is satisfying the classification rule, I'm happy and I'm not worried about any slack, and I'm defining the zeta j to be equal to 0. So this is an auxiliary variable which is just keeping track how much and how many of my points are not obeying the classification rule. Okay, so this is the idea. So zeta j's are positive numbers, and when zeta j is positive, that means that one of my points is not obeying the classification rule. And the size of zeta j is telling how badly I'm on the other side of the separating gap. So you can compactly write this definition of zeta j to be the maximum of the two numbers 1 minus cj qt xj minus p and 0. And so this is either 0, you have a point which is satisfying the separation condition, or it is positive and you want to then this zeta j is positive. And so if you want to find this separating hyperplane configuration, so then what you might want to do it in such a way that as few points as possible end up on the wrong side of the separating gap. So we are not that interested in a sense how far away on the wrong side a point is, because we are doing, after all, we are doing the classification. So classification is successful if the classification is done right for most of the points. And how badly a point fails to be on the right side of the hyperplane is not that important, because misclassification is misclassification regardless of how close you are to the gap. So rather than thinking that this zeta j, let's say square sum, should be smallest possible, we are actually interested about sparsity. So we want to have this vector zeta j to be sparse. So as few points as possible end up to the wrong side of the separating gap. So the more zeta j's are 0, the better. The vector zeta should be sparse. So that's the upshot here. So really we are looking for a slack variable which should be sparse. Now in optimization and in inverse problems and imaging, we know how to promote sparsity. And promoting sparsity means that you are trying to make the L1 sum of a vector as small as possible. So this is a well-known principle that is behind most of the sparsity promoting algorithms, including compressive sensing, and if you have come from statistics, you know probably lasso algorithm. So it is, and in geophysics there are other names for this principle. So if you want to sparsify a vector when you're doing optimization, the way to do that is to penalize the L1 norm of the vector. So what is the L1 norm of this vector zeta? The zeta vectors are non-negative, so I don't have to worry about the absolute value of zeta j, so they are non-negative. So the L1 norm of the zeta vector in this case is simply the sum of zeta j's. And so instead of just minimizing 1/2 times the length of Q, which is maximizing the gap, I'm also penalizing for having misclassifications. So I'm penalizing for ending up having lots of points on the wrong side of the gap. So as in optimization and in ill-post and problems where you do regularization, we, instead of minimizing simply the 1/2 of Q